So these are your atom notes part 1, in which we went over in class most of this, but there is some new stuff in here that you need for the activities you're doing, as well as the upcoming labs. So atomic theory in a brief, we've gone over this with Democritus saying that matter is made up of mostly empty space in which atoms move, and those atoms are solid, indestructible, and invisible. He also said that different kinds of atoms have different sizes and shapes. So for example, helium atom and a hydrogen atom have different sizes. They also have different shapes. We also said that this young gentleman or scientist was proven wrong later in years by John Dalton. Now, John Dalton, many, many years later, came around and said, well, all matter is composed of atoms. However, atoms of given elements are identical in like their size, their shape, and their chemical properties. He also said atoms cannot be created or destroyed. So when you look at this, here's your oxygen atom. It's the same size, same chemical properties, same mass as this oxygen. And these hydrogens are the same size, same mass, same chemical properties as these hydrogen. And hey, look, this hydrogen and or these hydrogen and this oxygen didn't just be created and it's not being destroyed, it's changing into this water molecule. So that was his take on everything. Now, Dalton also said that, hey, nothing is smaller than an atom. Atom is the smallest that you can go. And then along came J.J. Thomson and said, you're wrong, Dalton. He used the cathode ray tube and discovered there is something smaller than an atom. It's an electron. And so then he proposed his plum pudding model saying, hey, this is what an atom really looks like. It looks like that pudding, which is all positively charged. It's an all evenly positively charged. And then inside are raisins, which are negative. So these negative little pieces, or those, what he considered raisins, were your electrons. Then Rutherford came along and did a gold foil experiment that said, guess what, Thomson? You're wrong. The plum pudding model is not correct because there is a nucleus in the center of the atom. So he said, no, your plum pudding where everything's possibly charged and the electrons are in it are wrong. The electrons are outside this nucleus. After that came Bohr, and he's given us the most current model today. Bohr gave us the Bohr's diagram, which is what you'll be practicing. He says that there are 2 electrons in the first shell, 8 electrons in the second shell, 18 in the third, and so on and so forth. And so this is what it looks like. When we go and write things, though, you'll see hydrogen, lithium has 2, or helium has 2, lithium has 3, 2 in the first shell, 1 in the second. Notice carbon, 2 in the first shell, 4 in the second shell, and none of them are paired. Until we get to fluorine, notice that they are pairing. By neon, they are all paired. We are going into the next shell, and you'll see the bottom shells till we get way over here, all 8, and then we go to the next shell. Atomic structure, which we've been through. You should know this by heart, hopefully. Neutrons, which are bigger than protons and have a 0 charge. Fun fact, the neutron is actually a proton and electron combined, which is why they have a 0 charge and why they are slightly bigger than a proton. A proton is a positive charge and an electron is negatively charged and very, very, very small. Atomic number versus atomic mass. Atomic numbers right here, it tells you the number of protons as well as the number of electrons. And then you have your element symbol and then your atomic mass here. Your atomic mass is always 4.003 or 12.001 or 1.001 or 14.01. It's whatever, it will have point something. And that's in AMU, which is atomic mass unit. Now over here in carbon, you'll see atomic number, element symbol, and then atomic mass, which is atomic mass unit per atom. However, when we get later into chemistry and we start doing the math, we're going to talk about molar mass. And molar mass is 12.011 grams per mole. This is how you'll typically see it written. You'll have your mass numbers, your number of protons and neutrons right there. Your atomic number, which is your number of protons, has to equal your number of electrons in order for it to be a 0 charge, and we'll get into charges later when we talk about bonding. Your atomic symbol, which is right here. So then determine protons and electrons from a chemical symbol. We have carbon, 614. Protons are here 6, electrons are 6, unless there's a charge, there would be a charge here, but since there's no charge, I know that it's a neutral atom. So 6 and 6, and then the neutrons is 14 minus 6, which is 8. Now if you've done carbon, you should have a red flag saying, wait, isn't carbon 12? And isn't it the neutron 6? Yes, you are correct. The thing is this is an isotope, in which I'm going to explain in just a moment. Nitrogen down here, 7 protons, 7 electrons. If we take 15 minus 7, it is 8. Again, you're like, wait, Miss Crandall, hold the phone. Why is it 8? Why is the atomic mass 15 when I know it's 14? Again, this is another isotope, and we're going to get into that now. So isotopes versus allotropes. Isotopes are atoms of the same element with different number of neutrons, where allotropes are forms of the same element but are bonded differently, so they have different structures. So if you look over to this chart right here, allotropes are different forms of the same chemical element, where isotopes are different forms of atomic structure. Make note, this is different forms, this is different atomic structures in the same chemical element. Um, allotropes describe molecular structures, where isotopes describe atomic structures. Allotropes' molar mass can be either equal or different from each other. But in isotopes, the atomic number is the same, but the atomic mass is different. Allotropes are not found in all chemical elements, where isotopes are found in almost all chemical elements. Allotropes are chemical properties are different from each other, where isotopes, the chemical properties are similar. In allotropes, the stable molecules that are found naturally, and then in isotopes, some are stable while others are not. But you're like, Miss Crandall, this makes absolutely no sense still. I'm still completely lost. So let me give you examples. Example of allotropes. This is carbon right here. And allotropes this is all carbon, but they are bonded differently. So carbon is a diamond, but because of this is why we call it a diamond, because of this bond. Graphite, that's in your pencil, this is how it's bonded. So it is different, but it's still carbon. You have your buckyball over here. Still carbon, just looks different. And then your carbon nanotube, again, same, but is formed completely different. Where the isotopes of carbon, you've got carbon 12, carbon 13, carbon 14. Again, on this one, the structure is different. This one, the atomic structure is different. So carbon 12, 6 protons, 6 neutrons. Carbon 13, 6 protons, 7 neutrons. Carbon 14, 6 protons, 8 neutrons. So the neutrons are different in isotopes. And carbon 14 is what we are using for carbon dating. And that is the end of part 1 of your lecture.